Okay, I'm going to go through the final exam review and how I got each of these answers that are on my answer key. So one, it says balancing the following equation and identify the type of reaction. So you can see I called this a synthesis reaction because I have something plus something else turning into one thing. So one compound or element plus another element or compound. If it turns into one single product, that means I put them together, and that's the definition of a synthesis reaction. Now, how did we balance this with 2, 1, 2 coefficients? I will show you that part right now. So I have FeOH2 plus H2O2 turning into FeOH3. So you can see I cut this in half at my arrow. That means that according to the law of conservation of mass, everything that goes in must also come out. It's just going to look a little bit different. So we have FeOH, OH, HH, and then FeOH 3 times. Okay, so I have one Fe on both sides, that's balanced. I have 1, 2, 3, 4 oxygens, but I only have 1, 2, 3 oxygens on the right. I need another oxygen, however I cannot only add one more oxygen. I have to add a whole nother compound here. Okay, so then I have 1, 2, 3, 4, 5, 6 oxygens, and I have 1, 2, 3, 4. That means that I need 2 more on the left side. I can either add another FeOH2 or I can add another H2O2. So, deciding which one should be better, well, I added another Fe, which means I'm going to need another Fe on this side anyway, so I probably want to add an FeOH2. 6 oxygens, 6 oxygens, 6 hydrogens, 6 hydrogens, 2 irons, everything's balanced, so I've put a 1, 2 coefficient in the first blank, just a 1 coefficient in the second, and once again a 1, 2 coefficient. I just count them, how many times I used each one. Number 2. Hold this down a little bit. Number 2. I called this a combustion reaction. That's because I have a carbon and hydrogen plus oxygen turning into carbon dioxide and water. Anytime you see that carbon dioxide and water, that's evidence of a combustion reaction. Now, how did we get these coefficients? C2H6 plus O2 turns into CO2 plus H2O. So I cut that one in half, draw out what I see. I have 2 carbons on the left and only 1 on the right. I need another one, and it comes with 2 O's. I have 1, 2, 3, 4, 5, 6 hydrogens. I currently have 2, so I'm going to need to add 4 more. Now I have 1, 2 oxygens, 1, 2, 3, 4, 5, 6, 7. So if I add more oxygens, I'm going to quickly realize that there is no way for me to get 7. I either have 6 or 8. So now I've gone over in the number of oxygens I need. That means I'm going to need more oxygens on the right side. Well, I know I can't have an odd number of oxygens because I'll never be able to make an odd number of oxygens with this O2. So I'm going to add another water. That gives me 8, but by adding these 2 hydrogens, that means I need another C2H6. Now this gives me a total of 12 hydrogens. 2, 4, 6, 8 means I need 4 more hydrogens. So now I have 1, 2, 3, 4 carbons. 1, 2, need 2 more carbons. So my carbons are balanced, my hydrogens are balanced. I currently have 8 oxygens on the left, but I have 2, 4, 6, 8, 9, 10, 11, 12, 13, 14. So if we add a few more oxygens here, I get 2, 4, 6, 8, 10, 12, 14. So I need a 2 in the first blank. 1, 2, 3, 4, 5, 6, 7. I had 7 pairs of oxygen, 4 carbon dioxide, and 6 waters. That's how we get that balanced equation. The last one that we'll do together here, number 3, is, it says it's a decomposition reaction. So the reason that it's a decomposition reaction is because I start with one compound and it separates into 2 or more elements or compounds. So I have one piece breaking into multiple pieces. It's decomposing. All right, how do we balance this one? This looks like it's going to be the easiest of the 3 to balance. So when I have these parentheses, I'm going to put Ni, and then I'm going to put ClO3, and I'm going to put it 3 times. Now keep in mind Cl is chlorine. A lot of people make the mistake of thinking it's carbon and iodine. No, those are chlorine, and it's one single element. Okay, so I have 1 nickel on both sides. I have 2 chlorines on both sides. But I have 6 oxygens and only 2 oxygens, which means I need 4 more, and that's it. That's how we get a 1, 1, 3 for our coefficients. Here, number 4, it says identify the type of reaction and predict the products. So, it's a single replacement reaction. We know that because we have an element plus a compound. You wouldn't be able to see the other side of that reaction, but anytime you see an element plus a compound, that's going to be a single replacement. And what that means is this element is going to replace a portion of the compound. Aluminum is a metal, so it's going to replace Hg, which is mercury, which is also a metal. So aluminum is going to replace mercury, and that's how you end up with Hg by itself. Now, how do we get this AlPO4? Because here PO4 has a 2 and some parentheses. How do you know you don't need that? Well, so I have Al plus Hg3, PO4, parentheses 2. This aluminum is going to replace the Hg, so we know Hg is going to be by itself. Now we have to figure out how are Al and PO4 going to fit together. So if you look at your periodic table, aluminum is in group 3A, or group 13, and everything in that group makes a +3 charge. You need to know that. Then if you look at the back side of your periodic table under the polyatomic ions, you'll see that PO4 has a -3 charge. And so anytime my charges are the same, they just cancel out. I need one of each. So I have 1 aluminum and 1 PO4, no parentheses, no number outside the parentheses, nothing like that. And so here's my answer. Number 5. Number 5, we get into some math finally. So number 5 says, according to the law of conservation of mass, what mass of F2 is needed when reacting 23 grams of Ki to produce 12 grams of Kf and 21 grams of I2 as shown in the reaction to the right. So when you see anything talking about law of conservation of mass, so 23 grams of Ki, I'm going to write that under 3, that 23 under Ki. 12 grams of Kf, I'm going to write that under Kf, and 21 grams of I2. Remember, my reaction arrow is kind of like an equal sign. And so the one missing is what I'm looking for. So if I add these two on the right together, that gives me 23 grams is equal to x plus 33 grams. 23. If I want to get x by itself, I just need to subtract 23 from both sides. And so my missing number is 10 grams. That's how we get that right there. Number 6 says, what is the molar mass of MgBr2? So we have Mg, there's only one. Then we have Br, and there's 2 of those. And so we're going to need to multiply these times the mass on the periodic table. So if you look at your periodic table, you'll find that the mass of magnesium is 24.30 and the mass of bromine is 79.90. So I multiply these. 24.30 times 1 stays the same, but 79.9 times 2 is 159.8. Now I add those together, and we get 184.1 grams per mole, because those are the units of molar mass. And so that's how we get number 6 right there, 184.1. Number 7, keep folding this so you don't see. Number 7 says, how many molecules is 1.43 moles of NaF? So this is my conversion, so I put what I know, or am I given, in the first box. So moles of NaF. Whatever I have, I need to get rid of, so I'm going to cancel out moles of NaF. I'm trying to find molecules, and so you should have some conversion factors that you went over, and so you can change moles into molecules using Avogadro's number. 6.022 times 10 to the 23 is equal to 1 mole. So numbers at the top I multiply, so 1.43 times 6.022 times 10 to the 23rd power gives us 8.6 times 10 to the 23. Okay, that's how we get that answer. Number 7. No, just kidding. Number 8. It says, what is the percent composition of lithium in lithium chloride? So the first thing we have to do is find the mass of our whole compound, lithium chloride. So Li, there's 1 Li. Cl, there's 2. 6.494. 35.45 equals 6.94. 70.9. We add them together. Gives us 77.84. Now we want percent composition. So how much of this whole compound is just lithium? So we're going to divide 6.94 divided by 77.84, and it's a percentage, so we multiply that times 100, and that's how we get this 8.9. And if you round it to 2%. Okay, number 8. Number 9 is a little similar to number 7, but not exactly. It says, what is the volume in liters of 33 grams of bromine gas? So this is another conversion. So I have grams, which means I need to get rid of grams. The only thing I can change grams into is moles. So you need to know that the molar mass is equal to 1 mole of Br2. So if I look up the mass of bromine on the periodic table, which is 79.9, and I multiply it times 2, it gives me 159.8. Now, I don't want to stop there because it's asking me for volume in liters. That's a 2-step problem because I can only change grams into moles, which means now I need to cancel out moles, and I can change moles into liters. So the last conversion factor you need to know is that 22.4 liters is equal to 1 mole. Now I divide 33 divided by 159.8 times 22.4, and that's how we get 4.6, and if you round you get 3 liters. Number 10. Number 10 says, what is the molecular formula of a compound with a mass of 108 grams per mole and an empirical formula of CH2O? So the first thing we need to do is find the mass of that empirical formula. So we get these numbers from the periodic table. We multiply, add it all together. I've shown you how to do that, so now we're just going to skip a step. And you get 30.026. So we are going to need to divide this 180 grams per mole that's given to us by the molar mass of this CH2O. And if you do that, you get like 5.99, which we're going to round to 6. Now that's not our final answer, as you can see. What that means is we need to multiply that CH2O times 6. So each element, I distribute this 6 to, and we end up with C6H12O6. That's my final answer. Number 11 says how many moles of Cu, so how many moles of Cu are required to completely react with 5.8 moles of AgNO3. So, put what I'm given first, 5.8 moles AgNO3. Now, if I want to change from moles to moles, I need to get rid of moles of AgNO3, and I need to find moles of Cu. So notice my moles are the same, but my formula is changing. Anytime you set up your problem and you have moles and moles with different formulas, those numbers come from your balanced equation. So for AgNO3, we can see that the coefficient is 2. And for copper, there is no coefficient, which means it's 1. So at 5.8 divided by 2 is how we get 2.9 moles of Cu. And number 12, so it says how many grams of H3PO4 are produced when 10 moles of water react with an excess of P4O10. Anytime you see that word excess, cross that out. That's extra information. It's required to tell you that, but it's extra information you do not need for your problem. So we set up what we know, 10 moles of water. You need to know that water is H2O. I need to get rid of moles of H2O, so I put that on the bottom. Now, I need grams of H3PO4, but I cannot change moles to grams and H2O to H3PO4 in the same step. So instead, I'm going to change to moles of H3PO4. This allows me to change my formula while staying in moles. And then my second step will get rid of moles of H3PO4. And I'll change it into grams of H3PO4. So, moles to moles, just like we said in the last problem, anytime you see that, you look at your balanced equation. For H2O, the coefficient is 6. For H3PO4, the coefficient is 4. Anytime we have grams, we use the molar mass, and the molar mass is always equal to 1 mole. So notice these numbers are not 1 because they came from the equation. They could be 1 if the coefficient was 1, but they might not be. This opposite of grams will always be 1. Now we just need the molar mass of this, so we get these numbers from the periodic table. add them together. You get a total mass for this compound of 97.994. That's a decimal right there. Now we multiply. 10 times 4 is 40, divided by 6, then times, because it's on the top, 97.994. And that is how we get 653.3 grams for our answer. Okay, so this is the conclusion of this video. This is just page 1 of the review. You can find the other links to the rest after this.